Welcome to a new section on filter methods. In this section, I will cover a widely used method of feature selection, which is correlation. Correlation is a measure of the linear association between two or more variables. The higher the correlation, the more linearly associated the variables are. Correlation is often a useful property. If two variables are correlated, we can predict one from the other. Therefore, we generally look for features or predictor variables that are highly correlated with the target, particularly for linear machine learning models. However, if two predictor variables are highly correlated among themselves, they provide, in essence, redundant information about the target, because with just one of them, we can make accurate predictions on the target. The second predictor does not add additional information. Therefore, to make good machine learning models, in general, we look for variables that are highly correlated with the target, yet uncorrelated among themselves. In other words, we want the predictors to be correlated with the target, but the predictors should not be correlated among themselves. In fact, the central hypothesis of correlation feature selection is that a good set of features, this is, a good set of predictive variables, contains variables that are highly correlated with the class or the target, but uncorrelated with each other. You can read more on this in this PhD thesis. I added a link in the additional reading resources bonus section at the end of this course. Correlated features do not affect classification accuracy per se. The problem arises when we have datasets with loads of features, and in extreme cases, more features than examples. This is commonly known as the curse of dimensionality. If two numerical features are correlated, then one doesn't add much additional information over the other feature. So if the numbers of features is high, removing correlated features is a good approach to reduce the feature space without losing information. One thing, though, is that correlated features do affect model interpretability, and in particular, in linear models. If two variables are correlated, the model will fit coefficients to both variables that somehow capture the correlation. Therefore, this will be misleading on the true importance of each of the individual features. And this is also true for ensemble tree models. If two features are correlated, three methods will assign roughly the same importance to both, but half of the importance they would assign if we had only one of the correlated features in the dataset. I will come back to this point in future lectures. Therefore, removing correlated features improves both the machine learning models by making them simpler, with less variables, and yet similar predictive performance, and it also helps the interpretability of the model as it preserves the relationship of the feature with the target by removing the interaction with the correlated variable. Finally, different classifiers show different sensitivities to correlated features. Typically, linear models are more sensitive, and three methods are quite robust to correlated features. So how can we determine correlation? The most familiar and widely used measure of correlation is the Pearson's correlation coefficient. I present the formula for this coefficient here. This correlation coefficient can be easily calculated with most software, and is the measure I will be using in coming lectures. The Pearson correlation coefficient can take values between -1 and 1. A value of 1 means perfect correlation, and in general, positive values for the Pearson correlation coefficient indicate that the higher the value of variable 1, the higher the value of variable 2. A value of the Pearson's correlation coefficient of -1 indicates perfect anti-correlation if you want, or a negative correlation. In general, negative correlation values indicate that the higher the value of variable 1, the smaller the value of variable 2. For feature selection, the sign of the coefficient is not important. What we care about is the absolute value of the Pearson correlation coefficient. I will mention this again in the next lecture. I will show in the next lecture as well a practical example of how to reduce features by evaluating their correlation. For now, this is all. See you soon.